So in this problem, we're asked to find the value of an integral using a power series expansion of a function. And so the idea for that is that we just write out the number of terms that we need for the expansion and then just integrate them term by term. Since the series converge absolutely, we're able to do that, and our region of convergence, our interval of convergence, still stays the same after we integrate. So let's just see what we need in this particular problem. So we want to find the Maclaurin series of f of x is equal to the integral from 0 up to x of the sine of t dt. And we want to use term-by-term integration. Now here we're given the series expansion for sine of t over t, and we want to use 4 non-zero terms to estimate a value. All right, so let's jump in and see how we can do this problem. Well, if we weren't given that sine series, we know that our sine of t has a power series expansion with n going from 0 up to infinity of minus 1 to the n over 2n plus 1 factorial x to the 2n plus 1, or t rather, to the 2n plus 1. So if we wanted to, then just divide everything by t, what happens? So our sine of t over t then looks like the sum, n equals 0, up to infinity, minus 1 to the n, 2n plus 1 factorial, t to the 2n plus 1 divided by t. And so really this just gives us the summation minus 1 from 0 to infinity, minus 1 to the n, and then divided by 2n plus 1 factorial, and then t to the 2n power. And so that's where we obtain the series that they give us. So now if we want to approximate this with 4 terms, we just let n go from 0 up to 3. So if n is 0, that's going to give us just 1, then minus 1 over 3 factorial t to the second power, then plus 1 over 5 factorial t to the fourth power, minus 1 over 7 factorial t to the sixth power. So this gives us our 4 non-zero term approximation to our series. So now how do we actually do the integral? So now if we want to approximate our function f of x, being the integral from 0 up to x, of the sine of t over t dt, well, we can use the integral from 0 up to x and then the 4 terms of our approximation. So we have a 1 minus a 1 over 3 factorial t squared plus a 1 over 5 factorial t to the fourth minus a 1 over 7 factorial t to the sixth dt. So here we're able to then integrate this. So this is an approximation. So we're able to integrate this term by term. And so we have just x minus 1 over 3 factorial times 3 x cubed plus a 1 over 5 factorial times 5 x to the fifth minus a 1 over 7 factorial times 7 x to the seventh. And so this gives us an approximation for our integral. So now if we want to then estimate f of 1/4, what we then have is 1/4 minus 3 factorial gives us 6 times 3 is an 18 times a 1/4 cubed plus a 1 over 5 factorial gives us 120 times 5 gives us 600, 1/4 to the fifth power, And then a minus 1 over 7 factorial times 7 gives us 35,280 times 1/4 to the 7th power. So what this gives us, if we just get a common denominator, put all of these together, is 720,030,299. Let's clean that up just a little bit so that it's a little more obvious what we're talking about. 720,030,299 divided by 289,0137,600. So then if we turn this into a decimal approximation, what we find, we get approximately 0.24913357, or rounded to 3 decimal places, 0.249. So I hope you've enjoyed this. I hope it's been kind of instructive on maybe how we get the series and then how we're able to approximate an integral using that series. And I will see you guys next time.